but it looks that my presentation could be a little bit shorter because I mentioned some informations already that I have in my presentation as well. Because of my name, I'm originally Polish, right now living in Germany, so it's a Wojciech Nawrat, but it's quite perfect. The German doing it much worse. I would like to talk about this dependency between substructure and superstructure, or like mentioned by Neil, it's a platform in the slab tracks, because we see it as very crucial for installation of the slab track and the lifetime of the slab track. What are the requirements on the slab track, especially on the high speed? Also already mentioned, finally we expect the perfect alignment. To drive 300 kilometers, 350 kilometers per hour, finally the only requirement is the alignment. If we have the perfect alignment, the lifetime of the slab track will increase, will be longer, we get much less problems. And this is independent if we have quite straight alignment, if we have here something on bridges, here this very extreme alignment on Cologne-Frankfurt, which is following very close to the highway, or even restoration of the old tunnels. This also shown by May already, more or less, what interfaces do we have? We have interface to rolling stock, we have different type of trains, we have lines which are just high-speed lines. We have lines which, we have commuter trains with high-speed line combined. We have, then we have static dynamic interaction coming also for the different speeds, different trains. And airborne noise, tri-equipment. We have to install a lot of stuff in the track. We need the compatibility to signaling system, to power supply. But this is all stuff which we more or less can handle in the track. We know it. The only one we cannot handle anymore after the installation of the substructure is the substructure. If we don't make it correctly, we cannot correct it. We are lost. Here two major points is bearing capacity and expected settlements, and I would say the deformation. I would explain later why I see it a little bit wider. What are the characteristics of the slab track? What the operator later is expecting? Low maintenance availability. Of course, I'd like to operate it maybe 20 hours a day. I don't have time for maintenance. Increased service life cycle costs. We're talking about 60. In the meantime, 80, 100 years of operation of the slab track. Also here, low structure height and weight of the slab track. I'm able to improve or simplify the construction of the civil structures, bridges, due to the slab track, yes or not? Finally, high lateral resistance. We designed the tracks for 200, 250, 300 km per hour. Maybe later we expect to drive faster on those tracks. Finally, like mentioned, we expect a very good alignment. And can we be sure about it? If we build that track, can we ensure it for the client, for the operator? I think yes. This is very old graphic from the 90s. What it shows quality of the track in one section is 3 kilometers of the slab track, and this two showing adjusting ballasted sections. After the construction in 90s, the quality of the track is almost the same. The less the number, the better the quality of the track. But finally, the quality of the slab track remains the same. The quality of the ballasted track becomes worse and worse. After the tamping of renewal, you can improve it, but you will never reach the same level. But there is one secret behind it. This section is in the tunnel. We have very stable underground as well. It's not just the ballast, not just the deformation from the ballast. It's also very limited deformation in the slab tracks. So, how is the structure on the different substructures? In general, coming from the slab track side, you can divide the slab tracks in two major groups, families. One is all the concrete-based monolithic slab track system. It's if you take a radar, if you take a bugle, if you take a pour, let's say, all in the same level. The another one is a directly supported ballasted truck systems, which are based usually on the asphalt layers. They can be placed also on concrete layers, but here's no bond between the sleepers and the bearing structure. And now coming to the substructure, we have finally in total 3 different, already mentioned already, bridge, tunnel, earthwork. How is the bridge? Already since beginnings of the slab track or the beginnings of slab tracks on bridges, there is certain requirement, history, to separate the slab from the civil structure. Comes more from the safety reason in case of derailment, to be able to replace the slabs very quickly, so that we have kind of separation between the slab track and bridge infrastructure, and some fixing elements. Here for people who likes the typical engineering cross-section, more again the same picture. It's a bridge structure with protection layer. That depends on the bridge design. Do I need it? Yes or not? There are countries which do not require this protection layer and the slab structure, and here this level is separated. Important, there is no standard solution for slab track on bridges. I have always to design the slab track considering the properties of the bridge. Maybe for this short chain of single span bridges with 30, 32 meters, 24 meters, I can provide a standard design, but for the long bridges, if I like to avoid low expansion joints, I have to consider rate deflection of the bridge. There will be always a modified solution for the bridges. Tunnels, finally the perfect basis for the slab track. We have in a new tunnel is most probably hard rock abounded. The shell of the tunnel is also very, very solid, infill with the concrete. So here I do not expect huge problems with installation of the truck. So I can place the truck directly on the tunnel base. Problems, I would say the risk is very, very limited. But what's the most problematic? They are definitely the earthworks. If I try to construct the slab tracks on the earthworks, I have to consider multiple effects. How is the principal design of the slab track on the earthworks? I have usually the track slab, then I have the reductive bonded layer, and some layers below of it. It's a kind of multi-layer system where I'm distributing the loads from the top to the bottom, and have to distribute them to the load as well. So here in this area, fast standing system, slab, HBL, definitely no settlements, nothing. I can be almost sure about it. Problematic is this area. I have to take care about my substructure to do not lose in the fast standing, wrong way. To be able still to compensate in the fast standing system, but this is already mentioned, very, very limited. Let's go to the settlements deformation in the substructure. What can happen? Definitely the substructure is the risk of the owner. That's a quite straight situation. Our project in Greece, in Athens, we have done an investigation. Every 100 meters, take a look. But the Greek guy says always, if you construct something in Greece, you will find something. What we found here, it was quite important point of Greece. It was described in the old books. There's a point in Greece from where all the distances in Greece has been measured in the past. The guys stopped on the construction site for more than 6 months. There was no way to overcome it. So, just quite funny issue. But finally, what we like to express is the risk of substructure, that it has to be investigated in proper way. Also mentioned by Nay already, we need homogeneous substructure, and this is, let's say, comes from 2 points. One is the bearing resistance and dynamic stability of the substructure. And another is the limited settlements and other deformation in the track. Where the deformations come from? If we construct big abutments, I have the deformation in different points. One is the deformation of the subsoil in the bottom here, due to the weight of the embankment itself. Then the deformation or compacting of the embankment itself. And the last one is the deformation due to the dynamic loads of the train. They do not occur at the same time. I have to consider them. During the construction, I have just the first two. Constructing this embankment, I have settlements in the subsoil. I'm waiting, settling here. But what happens after the start of the operation? I have still settlements, but coming in all three parts. There's still some settlements expected here, still here, and the additional one coming from the load in the train, from the loads, vibrations caused by the train. How big they are, or which deformation do I have? Yeah, standard situation on the high-speed lines. We try to have a very, very smooth alignment. Means the number of the bridges, number of the tunnels is increasing. The embankments becomes bigger. So, in the cuttings, we can expect some heaves. In the big embankments, we have some settlements. Maybe over the culverts, they are more stable. I have less settlements. On the bridges, depends on the foundation, can be also different. Then we have some transitions areas. Tunnels, maybe we have some heaves in the tunnels as well, because we're removing material. So what we are doing, what we have to do, and this is important because this contract are usually separated. The slab track contract and the substructure contract, they are different. So I'm very happy to hear here that HS2 tries to see it as a combined system, to consider all the parts here. But finally, I have to make design for all my earthworks. What do I expect? What is the subsoil if I'm constructing the embankment? Then I'm doing really constructing, and then I have to wait. I have to wait if it settles. And then measure it. If this, what I've predicted, works. And then I check it, my deformations. If the residual deformations are smaller than the predicted. And this is the point that I can start to construct the slab track. I've spent 1.5 years in China designing the Wuhan to Guangzhou the line. And there was the famous question from the Chinese designer, how long we have to wait? 3 months? Or is definitely 6 months enough? It's like, no, you have to make an observation. Now, but we need a number. So there was discussion round and round. If we do not reach this requirement, maybe we can make some countermeasure, preloading, improvement of the substructure, where we have to investigate. Yeah, a lot of points, definitely, on each cuttings, on the transition areas, on embankments, not only 1, 2, 3 in continuous distances, on all foundations of the bridges. Yeah, also here transition to the tunnel itself. It's a lot of points what I need to see. So finally, on the earth structures, transition zones and backfill areas. And here on engineering structure, it is important to separate the settlements in the foundations of the bridges from the deformation of the bridge itself. Do not mix them together. Really take a look on the foundations, how much my bridge is settling, and later considering the deformation of the bridges in the slab track design. Yeah, the construction guys on the side are not really happy about it, because usually you use settlement leveling gauges which are fixed on embankments. You can see it here, and usually on quite stable known structures you can make it every 100 meter. If it's sensitive and you don't know really what happens, maybe you have to make it every 50 meters. And yeah, for the construction of the HS2 or even here in Nürnberg, Ingolstadt, you have a lot of points to see, to make an observation of them. Yeah, what is the result of this? You measure at the beginning, yeah, quite often, then you can reduce the periods of measuring. But finally, there is a curve showing the settlements or the residual settlements. Finally, I can say here, okay, at that time I see from this point, I expect here, yeah, less than 1 millimeter on the settlements. This is Cologne Frankfurt, yeah, quite reasonable settlements of 12 millimeters. Usually you can expect also settlements in, yeah, if the substructure is not so stable, also in centimeter and decimeter range. That's really quite good situation. But you see already here, we're talking here about a year or two until we can install Substructure on it. It's not that easy. Finally, what are the requirements? When I can start? If this is 1 centimeter, 2 centimeter, 5 centimeters, now imagine it's also as well. Finally, there is a requirement 1.5 centimeters of residual settlements. We can start with the construction of the slab track. In exceptional cases, we can allow 6, and mentioned by name is also reduced already to 3, if we can compensate it by vertical curves. And this means for speed of 300 kilometers per hour, a curve of 36,000 meters, so not that easy. Second point here, it's compensation in this range in the fastening system. It's also an economical issue. I have to go in the track, and also the components which I have to install in this track is also not that easy. So finally, we should focus on this part. All the modern fastening system has a high elastic fastening system. That's a typical stiffness for the high-speed line on the main lines, and they have certain horizontal and vertical compensation possibility. But some of them I have to keep from the construction itself, so only part of this remains for the maintenance later on. How it also usually it's a dismantling of the fastening system, introducing a kind of shims. Usually you can adjust the height in millimeter range, and assembling it again. Which situation you can compensate in the track? We have, for example, here typical the curve of the embankment. We have a dam. Here we have a cutting. Here most probably we expect some settlement. Here we can expect some heave. So here I can underlay some compensation plates to bring the track again to the position. But here I have to readjust my alignment and bring it again to the new level, considering this heave. What can be done as well? Maybe if you expect heaves, there is also a way to install the fastening system with a different arrangement, so that if the heaves that occurs, I can remove some plates, so that finally, in the final assembly, I have the alignment that I want. That's a little bit theory of that. I just like to bring the focus on the substructure, and would like to show you some cases that we faced already in the past. Heil Zuid in Netherlands. This was a project where we known from the beginning that the substructure is extremely poor. We have just a sand or something, nothing stable. So the decision was made to build so-called settlement free plates. Those are plates on 3.20 meters, I think, in the thickness of 500 millimeters, half a meter, with a pile foundation. You can see this here. Just to stabilize the substructure. The piles as deep as necessary to reach the structure which is able to bear it. Here you can see this, the piles, and finally here is the reinforcement for this settlement free plates, and these are the settlement free plates. And in this on top of this, we have installed the track. What has happened now? On the side of the track, the new highway has been built, huge abutment. And right now, the whole track starts to move sideways. Right now, they are in the range of 10 millimeters. The prediction shows that they will be 30 millimeters. We started quite huge development how to solve this problem, but there's really consideration also. Take a look left and right of the track. Nürnberg-Ingolstadt, you can see it's also the Nürnberg-Ingolstadt is following the highway A9 in Germany. Quite huge cutting, I think 5-6 meters, something like that. After removing the load and absorbing of the water from the soil started to lift up. The final measure, there was a replacement of the subsoil between 0.5 and 2.3 meters, covering it with the asphalt, providing some drainage to avoid the new water in it, and then starting construction of the slab duct with this typical frost protection layer, HBL track itself. The next one, also Nürnberg-Ingolstadt. Here is a small cutting, and here is so-called Auerberg. Very, very flat back hill. What has happened? This green one, it was material which tends to sliding. It was stable until this blue one was also not interrupted. Due to the construction of the small cutting here, it was weakened, I think. The guys on the side recognized this area starts to move, starts sliding. There was not an option. There's already, I think, some of this has been found on the track already. So, huge measure for stabilization of this small hill to prevent it to slide on the track. And last one, also from Nürnberg-Ingolstadt, castified regions. There's some hall rooms has been found in the track. It was a huge issue in the newspapers. There was I don't know, Yellow Press mentioned the German DB has to build bridges in the tunnels. But this was really an issue. We found a lot of them. A lot of simulation has been made to investigate how the embankments on top of this cavities works. Different measures with geogrids, with improvement of embankments has been made. But it's also made a huge influence on the construction of the design period. So Nürnberg-Ingolstadt was not that easy. So I would like to bring the focus of the owner to take care extremely on the substructure, because I think slab tracks are really good solutions for high-speed lines, but without the proper subsoil, we are not able to get the advantages of the slab tracks. Thank you very much.